So if I'm given a shape and then another shape that results from a dilation of the original shape, I should be able to calculate or identify what the scale factor is that was used. And then I should be able to use that scale factor or proportions to figure out the lengths of missing sides. So if I see this triangle, I can see triangle ABC to the right, and I see triangle A prime, B prime, C prime to the left. I understand that it's scaled, and it's increasing in size, and the direction of the scaling is from the smaller ABC to the larger. And that just has to do with the fact that we know that after a transformation we tack on the primes. So without that arrow even being there, I understand that I'm going from the smaller one on the left to the larger one on the right. Now, having said that, I understand that my scale factor has to be a number larger than 1 because I'm clearly increasing the shape. Now, if I was to say that this was 3 units long and this was 5 units long, my scale factor is the new or scaled up version divided by the the original shape. So my scale factor, you can see I land my new dimension is 5 and the original one is 3. So my scale factor is 5/3. Now if I think about that, I can take any of the dimensions of ABC, and if I multiply those dimensions by 5/3, I'll get the new dimension. The obvious one is the one that I have here. If I take 3, right, and if I multiply that by 5/3, I should get 5. And sure enough, 3 times 5/3 does indeed equal 5. So this is the scale factor that allows me to map between the original shape and the scaled up version. Let's say that I have a little bit more information on the triangle. I'll say that this dimension is, I'll say this is 4, 4, and a question could be, what's this dimension? And maybe I'll say this is y units long, and I might say that this is x units long. So now I have two additional questions. I'm asked to figure out the length of A prime C prime, which is marked with X, or I'm asked to find the length of CB, which is marked with a Y. And in both of these cases, there's actually two different and similar and related methods, right? I can take the one on my original shape, for example, the 4, and I could multiply that by the scale factor, and that would give me X. It would give me that length. Well, 4 times 5/3 would be 20/3, and I could say that that's what X is, right? X is 20/3, and that's a perfectly fine answer. If I wanted to, I could write it as a mixed number, or I could even give it as a decimal approximation. The decimal approximation is problematic because it's a non-terminating decimal. It's right. It's what is it? 6.666, a bunch of values of 6, and so probably 20/3 is the best answer. And again, I'm just using the fact that any dimension on my original triangle times the scale factor is going to give me the corresponding dimension on my new triangle. Now I can use what I just said to figure out the length of y as well. However, this time y is on the original shape, so I'm going to multiply that by the scale factor. So you can see I'm going original dimension y times my scale factor 5/3, and that has to give me an answer of 5. So now I'm solving this equation here to figure out what y is, what the length of y is. And I can get it one of two ways. I can divide both sides by 5/3, or also I can notice that if I take the number 5/3, and for example, I'll just squeeze this in here and I'll write it in a slightly different color, and I multiply this side by the reciprocal of 5/3 times 3/5 times 3/5. Well, it turns out that 5 times 3/5 is just the number 1, so I do get y on this side, and over on the other side I end up getting 3. So y, the length of this segment here, would have to equal 3 if this diagram was accurate. And that's kind of goofy. I should have noticed that right away because this was already a 5, right? So it would follow that these would have to be the same. And what's really goofy is that this is clearly not drawn to scale because neither one of these look like isosceles triangles. There's another way that's worthy of your consideration for solving these, and I think it's something that perhaps you did in the middle school quite a bit, and that's just writing a bunch of equivalent fractions. These all form proportions. So I could say, for example, I'll just go 3 over 5 is proportionate to 4 over x is proportionate to y over 5. And all I'm doing is I'm just looking at this, and in this case I'm taking the dimensions of the original shape and dividing it by the new. And there's no reason why I would have to do that. I could flip these as well, and this would also be equally true. What's nice about writing it this way is that now I can actually see my scale factor at the same time. Oops, I want to write x over 4. And then that equals 5 over y. Now, what's nice about this is that this actually gives me two nice proportions, and I can use those proportions to figure out what x and y are. So here's one of the proportions. And again, a proportion is just a fancy word. All it means is that you've got one ratio or fraction equal to another fraction. So 5/3 is equal to x over 4. When you have ratios like that, we can use fraction busters, or we can use the fact that if I multiply both sides by 12, the fractions go away, and it ends up becoming equivalent to 4 times 5 is equal to 3 times x. And again, there's nothing crazy or magic about that. Literally all I did was I thought about what would happen if I multiplied both sides of this by 12 times 12. And on the left hand side I noticed 12 divided by 3 was 4. That's why I got a 4 here. And on the other side I have 12 divided by 4 is 3. That's why I have a 3 here. So you can see that x is 20/3. So that's another way you can do it, right? You can find the scale factor and then use it to move from the original to the new, or you can identify the proportions and solve those to figure out missing side lengths.